Welcome, students. The topic of my presentation today is the principle of inclusion and exclusion. It is a topic which comes under the realm of combinatorics, which essentially is the mathematics of counting. You have encountered this topic in your syllabus. For example, the chapter on permutation and combination and the following chapter on binomial theorem comes under counting, comes under combinatorics. The topic I've chosen for today, the principle of inclusion and exclusion, is not a part of your course curriculum. However, we feel that it is a topic which is pitched at a level perhaps just beyond high school and is a valuable asset to solving a whole lot of problems that are within the realm of combinatorics. Let me give you an example of what would constitute a problem that can be solved using the principle of inclusion and exclusion. Without giving numbers, let us suppose we have a class of a certain number of students, some of whom study mathematics, some of whom study physics, some of whom study chemistry, and you're further informed that a certain number of them study both physics and mathematics, some of them study both physics and chemistry, and some of them study both mathematics and chemistry. Essentially, with this information and with one other bit, for example, either the number of students who study all three subjects or the number of students who study at least one of these subjects, you can deduce the other number. This is an example of the principle of inclusion and exclusion. We call this PIE, or pi for short. This is an example where we've applied pi to three sets. The situation with two sets is even simpler. And so perhaps I will like to begin with an example of what pi tells me for two sets. Let's say, for example, I have two sets, A and B. It goes without saying that all my sets are finite sets. When we are counting, we always assume the sets are finite. And we would like to figure out a relation between the union of the two sets, A and B, and the intersection. Now, there's a very simple relation between these two sets. If you look at the union of A and B and count the number of elements in it, and if you look at the intersection of two sets, A and B, and count the number of elements in it, and if you add the two numbers up, it is in fact equal to the sum of the numbers in each of the two sets. It's equal to the number of elements in A plus the number of elements in B. You might have noticed in some of your books the terminology called Venn diagrams. Venn diagrams is a geometric way of expressing these sets as a whole, and by a suitable choice of the picture, sometimes deducing a relationship between the various sizes of sets. For instance, in a picture like this, I could draw a little rectangular shape, and everything within that shape is called the set X. It is what you might call the universal set. So for example, when we're looking at the complement of sets, there is always something called the universal set. So the complement of A by itself is not well defined. It doesn't have a full meaning. It doesn't have an exact meaning. It has to be defined with respect to the universe. So the complement of A, for instance, with respect to the set X, would be the elements in X which are not in A. So bear in mind that if the universal set is not mentioned to you, the complement of the set has no real meaning. So let me draw this X within this box. Let me draw two hypothetical sets, A and B. Put them within this oval or circular shape. It is understood that whatever is enclosed by that shape within A essentially measures the number of elements in A. The same goes with B. And I've drawn a picture as if the two sets intersect. Of course, they may not, in which case the picture would be slightly different. But the The usual way of interpreting this or drawing this as a Venn diagram is to make them intersect. Well, as I said, everything inside the circle here contains A, contains the elements of A, and everything inside the circle here contains the elements B. The union of A and B would then be, and I'm going to write it out here, the elements enclosed by the periphery or the boundary of the shape. So it goes something like this and then continues like this. And that would be A union B. If you think of the three regions here, and I label them by the Roman numerals 1, 2, and 3, then the union of A and B would be what is captured by the three regions together, 1, 2, and 3. The intersection of A and B would be captured by the region enclosed by region 3. I write this here to the left side. And what is mentioned in the equation that I've written can be captured by just looking at the Venn diagrams and relating the two sides to the regions they represent. So for example, if I look at the left-hand side, if I look at the union of A and B, the union of A and B is represented by the regions 1, 2, and 3. The region represented by A intersection B is just 3. So the left-hand side is captured by the regions 1, 2, and 3 counted twice. On the other hand, the region A is represented by the regions 1 and 3 together. The region B is represented by the regions 2 and 3 together. And therefore, if you add those two numbers up, you will get the regions 1 and 2 and 3 twice. This, therefore, is a geometric verification of the formula that I wrote down. It is not an algebraic verification. And mathematicians tend to downplay this as being not a very precise verification of results. Nevertheless, it serves as a very good first step towards solving problems that involve counting of two sets. Let's look at one more version of this, the version with 3 sets. The pictures become a little more complicated. Let me first draw my universal set and enclose it in a rectangle as I did before. Now let me draw my 3 sets represented by 3 ovals or 3 circles and call them A, B, and C. It's probably important now for me to put a little label on each of the regions that is enclosed here. So let me begin by calling this region 1. By this region I mean, and let me trace this out by my pen, similarly, let's call this region 2, and by this I mean the region traced out by this periphery. Let me call this region 3. This is enclosed by the following boundary. Let me call this region 4. So this is traced out by this boundary. Then let me call this 5. It's traced out by this boundary. This one is 6. This is traced out by this boundary. And the final one that I haven't written is the one in the middle, which is 7, which is traced out by this boundary. As a matter of fact, there's one other region that is enclosed by this picture that I've not written out. I could call that 8. And this is the region outside of A and outside of B and outside of C. In terms of set theory or set theoretic notation, each of these regions can be interpreted as a set. So for example, A would be the set which contains elements enclosed by, and these regions are disjointed regions, which means that no two of these regions intersect. So 1 and 4 and 5 and 7. I could have used the standard number system 1, 2, 3, 4, but in fact I'm going to plug in numbers to represent the number of elements in each of these sets. And therefore it's useful to stay away from numbering these regions by the same numerals that I would use to denote the size of the sets. So these are the Roman numbers. Luckily I'm not going beyond 8, and therefore it should not be too much of a task to remember what these things are. So A again is captured by the regions within 1 and 4 and 5 and 7. B, I'm going to write it right here, right under this. B is captured by 2 and 4. I'm trying to write this in a sequence. 6 and 7. And C is captured by 3. Let me just try to squeeze this in the margin. And then 5. And then 6. And finally, I hope this squeezes in, 7. So those are the regions that make up A, B, and C. Now, these are expressions that involve 4 regions for each of these sets. If I take the innermost region, the region marked 7, that is common to A, B, and C. You can see that pictorially, or you could even see it according to the equations I've written down to represent the regions. Therefore, the central region here, 7, is actually the intersection of A with B and C. In other words, A intersection B intersection C. You can similarly give set theoretic notation to each of the other regions, which I'm not doing just now. Let me write down a formula corresponding to what I wrote down for the 2 set version that I get for the 3 set version. So let me remind myself what I did for the 2 set version first. A union B plus A intersection B is equal to A plus B. What I meant, of course, was the size of those sets, not just the sets. Let me write this in a slightly different fashion, the one I want to use for pi. The number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. This is pi in the direct version. By direct version, I mean the version that tells you the size of the union of 2 sets. I can turn this around. I can make a small change here and talk about, so let me write this as direct version. Talk about the complementary version. So in the complementary version, I will look at the size of the complement of A union B. That slash there denotes the complement of A union B. And the reason that X is written is to remind ourselves that we're taking the complement with respect to the universal set X. Some books are used to calling this symbolically as A union B to the power little c for complement. This is actually the number of elements in X minus the number of elements in A union B. This is because the number of elements in X minus A union B is simply the number of elements in X minus the number of elements in A union B, as A union B is contained in X. In general, if you take the difference of 2 sets, it's not true that the number of elements in A minus B is the number of elements in A minus the number of elements in B. But it is so in this case because A union B is contained in X. So if I may go on and plug this result into the previous one and substitute A union B, I get number of elements in X minus, and I subtract number of elements in A plus the number of elements in B minus the number of elements in A intersection B. And I open this bracket up in the next line, and I get number of elements in X minus, and I prefer to write this together, number of elements in A plus number of elements in B, but separate out the last term. So this is the number of elements in A intersection B, and now this comes with a plus sign. So there are two things to note out here when I take this particular formulation of pi. One is that the signs in these formulae alternate. We begin with a plus, and then we take minus, and then we take plus, and we keep going. In this case, there are only 3 terms. But as you increase the number of terms in the sets, the number of sets, there will be more of these coming in. There will be more alternating signs coming in. The second thing that you observe is that, in a sense, the first element is devoid of using any A's and B's. It's like taking A's and B's 0 at a time. The second expression there involves taking the sets 1 at a time. You're adding the number of elements in A to the number of elements in B. And in the last term, you're taking them 2 at a time. You're taking the intersection 2 at a time. You can't, of course, have any more terms because there are only 2 sets. And therefore, there's no concept of, no question of taking sets 3 at a time. The reason I mention all this is because I'm now going to try and extend this to 3 sets, which I'm going to call A, B, and C. So let's say I have 3 sets A, B, and C. And I look at the union. What would my union be? Well, my union would be number of elements in A plus the number of elements in B plus the number of elements in C. These are the terms that involve the sets taken 1 at a time. I will write the next level below, put a bracket here, take the sets 2 at a time, A intersect with B, A intersect with C, and B intersect with C. All these terms have to be subtracted. Finally, the alternating sign, I put a plus, and now I take the sets 3 at a time, but there's only one way of doing it. I put all of them together, and what emerges is the analog of what I had for the 2 version set. I wrote down a formula for A union B in terms of A's and B's and the intersection. Well, what I'm doing here is a little more complicated because I have 3 sets. So I'm now writing down a version for the size of A union B union C in terms of the number of elements in A and B and C, and then in terms of the sets, intersection of sets taken 2 at a time, and finally in terms of the intersection of the sets taken 3 at a time. If I may also get the indirect version or the complementary version, this is the direct version, I would try to figure out what is the size of the complement of 3 sets A, B, and C. Again, I may use the notation A union B union C, complement. I've used 2 different C's here, hopefully. One is a big C, which is a set. The little c is to the superscript, the power. This would be the number of elements in X minus the number of elements in A union B union C. And of course, I'm simply then going to plug in the formula that I just wrote down for A union B union C to complete this. So at the first level, I'm going to be subtracting from the size of X or the number of elements in X the 3 terms A, B, and C, and then I'm going to be adding the 3 terms taken 2 at a time, and finally I'm going to be subtracting the only term that I can get. I didn't have to write the bracket there. A intersection B intersection C. That bracket is superfluous, but anyways, so this is the complement version. Not sure if I wrote this in the 2-set version. You could add it in if I forgot to write it. So this is the complement version. In other words, it tells you the size of the complement of the union of three sets. A typical place where that could be applied is the situation where you want to know how many elements are in none of the three sets A, B, and C. Let me now look at a couple of examples. One example for the situation with two sets and one for three sets. I have a problem written up here. It saves me the time to write this down. It's a fairly straightforward problem. Let me read the problem with you first. Among 60 pet owners responding to a survey, 30 owned cats, 25 owned dogs, and 5 owned both. How many respondents had a cat or a dog? What is missing in this is the understanding of the word or. When we say how many had a cat or a dog, it includes the situation where somebody, a respondent, had both a cat and a dog. In other words, at least one of a cat or a dog. The second question is how many had neither? This can be done in both ways by drawing a Venn diagram picture, which is often what you tend to do. Let me try to squeeze this into the frame. If I'm missing a problem, that's fine. And I have this picture out here. So I have this universal set X, and I have these two sets. I will call the first set C and the second set D. It would probably have been simpler to use A and B, but I think it's more natural to use C and D. Obviously, C is a set which talks about the pet owners who owned a cat. D is a set that talks about the pet owners who owned a dog. Now, the first thing I notice out here is that there are 60 pet owners responding to the survey. So I could put in somewhere the number 60 against X. It is the size of the entire box of the entire universe in this particular situation. It also says 30 owned a cat. And therefore, I know that if I might term the regions as I did before, 1, 2, and 3, with 4 the region which is in the complement, then I know that 30 corresponds to the sum of the numbers that I need to put in under C, and therefore 1 plus 3 is what 30 is. Similarly, I know that the regions 2 and 3 represent the dogs, and therefore 2 plus 3 should be equal to 25. I'll store that in memory for just now. I'm going to work backwards because I don't have a clear idea of what's going to happen to 1 or 3 or 2. But the last data that I have says 5 owned both. So that gives me an idea that the region 3, which represents the intersection of C and D, must be 5. And now I can back calculate. I know that the number of cat owners is 30. So 1 plus 3 is 30. So I could fill in 25 in the region 1. Similarly, I have 25 dog owners. So 2 and 3 is 25. And therefore, I could put in 20 in this region 2. Let me go back and see what question I had to answer. There's only one thing that I haven't filled. So 60 was the number which was the total. I'll just put that in a box to remind myself that that's the total. It is not representative of how many go into region 4. Let me put that in. How do I get that? Well, 25 plus 5 plus 20 represents the sum total of C and D. In other words, the union of C and D. If you add the 3 numbers up, you get 50. It leaves you with 10 solely for the outside of C and D, or the complement of C and D. Complement of C union D, I should have said. So to get back to the question is how many respondents had a cat or a dog? So if you had a cat or a dog, you would be talking about either or, and you'd be asking the question, what is the size of the set C union D? Well, that is 25 plus 5 plus 20, which is equal to 50. So the answer to that question would be there'd be 50 people who had either a cat or a dog or both. The second part to this is how many had neither a cat nor a dog. So that would be C union D. I put this within bracket and put a little c there for complement. What I've been calling the number of elements in X minus C union D. In this particular picture, represented by region 4. And how many do we have there? Well, we had 60 minus 50. We've done this before. So I will simply write down 10. I could also, of course, have done this in a fairly straightforward manner by just invoking the formulae. If I were to invoke the formulae here, and I will write right below the problem, because then you can read the problem as well. Let's look at C union D. I know this to be C plus D minus C intersection D. And now I kind of do exactly what I did before. I fill in what I do know first. C intersection D is equal to 5, because it said 5 own both. But now think about it. Did I really need C intersection D to fill in the C and D? No. Because the way the problem was phrased, I already knew in the problem itself what C's and D's were. C was the total number of cat owners. That is 30. So I fill this in. D is 25. And therefore, I get 50. Fairly straightforward, in some sense simpler than what I did by a Venn diagram. Because in the Venn diagram, I had to go to regions, separate the regions out, fill in data that was not necessary to solve this problem. What happens to the second part where I needed the complement? This is equally straightforward by the formulae. I write down the number of elements in X minus the number of elements in C union D. I know the number of elements in X to be 60. I've just found the second one out to be 50. And therefore, this is 10. And that answers the second question. Let me take another problem which is slightly harder. The second problem involves 3 sets. I've taken larger numbers, so I'm going to let you do the calculation yourself. And I've taken something which is topical. It's nothing to do with cats and dogs, but more to do with 3 letters that you're probably familiar with. You can guess why I've chosen those 3 letters. M stands for mathematics, P stands for physics, and C stands for chemistry. Let me read this problem out to you. It says a total of 1,232 students have taken mathematics. Wherever I see the letter M, I'm going to read out mathematics. 879 have taken physics. 114 have taken chemistry. And we further know that 103 have taken both mathematics and physics. 23 have taken both mathematics and chemistry. 14 have taken both physics and chemistry. The last part that is required to solve this problem is you're given that 2,092 students have taken at least one of the 3 subjects. And from there, you have to deduce how many have taken all 3. Notice there is nothing mentioned about the class size or the survey size. And therefore, we will never be able to deduce the number of students who've taken none of the 3 subjects, because that inherently depends on the size of the class. So this is more a direct problem, a problem where you have to figure out how many have taken at least one, therefore the size of the union of P, C, and M. I have a little Venn diagram here to represent that situation. As you can see, this Venn diagram involves many regions and therefore becomes a little more complicated. The universal set X in this particular instance is not essential to the problem, but I've put this in by force of practice because I tend to do it. This thing on the left is mathematics, the thing on the right is physics, the thing on the left or the bottom is chemistry. And then we try to put in the numbers as best we can. Let me try to put this in. But for this, I probably need to kind of have the full data, or at least part of it, to help me along. The trick to filling up these numbers is to go backwards, is to kind of put the numbers from the region which is common to all of them first. Can I do this? Well, do I have information about what is common to all three? Well, the question says, how many have taken all three? Well, that's what I need to know, so I don't know that. Let me put this little x out there. X denotes the number of elements in what is common to all three. Let me read on and see what I can do, reading backwards. The data says 14 have taken both physics and chemistry. Now, physics and chemistry is contained in the region that is in here. The two together make up 14, so we can deduce that this region itself is 14 minus x. The other data I read, the next data I read is 23 have taken mathematics and chemistry. So mathematics and chemistry is enclosed by these two regions. This is x, so therefore I've got to write slightly smaller perhaps. 23 minus x comes in here. And then the first data in the segment says 103 have taken mathematics and physics. So that is enclosed by this segment here. So this thing here would be 103 minus x. I've filled out 4 of these 7 boxes, 4 of these 7 ovals. What are the 3 remaining ovals? Well, you have a total of 1,232 students who've taken mathematics. A little bit of addition to be done. This number here that I'm going to fill in will be, and I will let you do the calculation, 1,232 minus the sum total of what you see in these 3 regions. So if you add up 23 minus x and x, you get 23. You also have to add to that 103, so that's 126 less x. And if you simplify that, you will get 1106 plus x, which I'm not writing because I'm going to run out of space. And that's a calculation that you can work out yourself. What about the physics? There's 879 who've taken physics. So I'm going to write 879 here. And I'm going to subtract. And much the same way as before, these 3 regions here add up to 117 minus x. And whatever 879 minus 117 minus x is, goes into that little slot there. What about chemistry? Smaller numbers, easier for us to handle. 114 minus, and you sum the numbers in these 3 regions, and you can see you get 37 minus x. So as I said, you can do the calculation yourself, a little bit of addition and subtraction. And now you've got all the 7 regions filled up individually. All you've got to do is add the numbers algebraically in those regions. You will get some constant plus something x, or some constant minus something x. You'll get some polynomial in x, linear. And that will represent the total number of numbers within P, C, and M. In other words, that will represent P plus C plus M. And you know that to be 2092. So I'm simply going to write adding algebraically these 7 numbers and equating to 2092 gives x. And it is x that we sought, because x was the number of elements which is common to all 3. Of course, I could have done this directly. And as before, you'd probably recognize that writing this as a formula would have been an easier task. Let me attempt to do this directly. So let me put this data in here. Or let me write the equation, and then I'll put this in again. So what is the version concerning 3 sets of pi? A union B union C size of is A plus B plus C. Minus things taken two at a time. So I will go A intersection B, A intersection C, and B intersection C. And finally, I'll add back. I've again put the bracket, which I didn't need to. A intersection B, intersection C. Having put that bracket, I better close it. And that's the formula. And all one has got to do is plug in these numbers. And as I said before, in a problem like this, or in most problems, in fact, you didn't have to fill in the details. You didn't have to fill in the numbers in each of those regions. It is, in fact, much more expedient, much simpler, much more direct to use the data that is given to you into these formulas, and the answer comes out fairly readily. Let's look at this particular example to illustrate that. What is A union B union C? Well, it's the number of people, the students, who've taken at least one of these three subjects. I erred a little bit in the notation. I should have written M, P, and C. Instead, I wrote A, B, and C. But you probably can figure out the correspondence. C can still stand for chemistry. And let's say that A stands for M, or mathematics, and let's say B stands for physics. Well, what are the numbers here? The numbers are, on the left-hand side, the number of students who've taken at least one of them. We know that to be 192. So that goes into the left-hand side. In the first line of the right-hand side, I have to add the number of students who've taken at least one of these subjects. There is 1232 who've taken A, which is the same as M. There's 879 that have taken P or B, and 114 who've taken C. At the second level, and I subtract all three of them, there's 103 who've taken M and P. There is 23 who've taken M and C, and there is 14 who've taken P and C. Finally, I have to add back. Well, I don't know what this is. This is what I have to find out. So I have to add back what I called X earlier. Now, this is a purely numerical exercise, which I will let you work out. I believe that if you work this out, you get 7 is equal to X. So check this calculation, and you will agree with me that if you knew the formulae rather than relied on Venn diagrams, you'd be better off. Let me get to the crux of the issue, the main problem at hand, which is the principle. So there are two versions to the principle. There's the direct version and the indirect version, the complementary version. I tend normally to do the complementary version first. I will first display the version. It's written in a fairly compact, precise, short form, and some of the notations will require a little bit of explanation before I go into the proof. As I said before, there is a universal set. I've called this X. I've assumed X is a finite set. Otherwise, there's no counting that happens. I have a collection of non-empty subsets of X. If any one of these subsets is empty, the formula is still valid. But it doesn't really come into the picture in the equation, so you may as well not have it. And therefore, I've assumed that these sets are all non-empty. They're subsets of X. The left-hand side of the equation there counts the number of elements which is in the complement of the union of the AIs. The left-hand side is simply the set difference of X and the union of the AIs. In other words, it is the number of elements which is in none of the sets A1 through AN. This is fairly straightforward in terms of notation and what it asks. It is the right-hand side which requires a little bit of explanation. Some of it is given right there. Perhaps some is missing. So there are several terms here that you're summing over. You're summing over a set. The set is something that I call I. you need to think of I as being an indexing set, as a set of numbers, as a set which takes none or some of the numbers between 1 and n. So what is I a subset of? It is a subset of something that I've written in square brackets, n, which in combinatorics denotes the set of the first n positive integers. So the square bracket n is simply the set 1, 2, 3, and so on till n. So the sum is over all subsets of this particular set n, square bracket n. Bear in mind, this includes the empty subset. So I could also be the empty subset. Now this is what we are summing over. In other words, for each such subset of square bracket n, and there's 2 to the power of n such subsets, there is effectively a single term to evaluate. And at the end of the day, you have to add up these 2 to the power of n sums to evaluate what is on the left-hand side. Now that may look a little bit scary, particularly if n is large, but it really is not, because most problems have a little symmetric version, and many of those arguments can be clubbed together. Let me see what is to be summed first. So the term that has to be summed corresponding to a typical subset I of this n set, or the set square bracket n, is first minus 1 to the power the number of elements in I. So if the number of elements in I is even, that term is plus 1, and if it is odd, it is minus 1. You can already begin to see that pi has that plus minus sign, and that is incorporated in this general version. Now what is this plus minus going to be multiplied by? It's something that we will call a sub capital I. So first we evaluate, or we decipher what is meant by a sub capital I, and then we count the size of that set, count how many elements are in that set. What is a sub capital I? Well, a sub capital I is simply the intersection of all those ai's where I belongs to I. So for example, if capital I was a set 1, 2, 3, then a sub capital I would be A1 intersection A2 intersection A3. So it's fairly easy to understand what is meant by a sub I, a little harder to figure out what that size of that set would be, except that I still have to explain what happens if I was to take I to be the empty set. Well, there are ways to justify why this should be the definition, but I won't go into that just now. Let me just assume that we set by convention or by definition that when I is the empty set, a sub I or a sub empty set is going to be taken as the whole set. You might be tempted to think that this should be the empty set, but no, it really should be defined to be and is defined to be the entire set X. So let's just take for granted that corresponding to I equal to the empty set in that summation on the right, the term is minus 1 to the power of number of elements in the empty set, which is 0, and therefore plus 1, multiplied by the size of a sub empty set, which is the size of the set X. And you might remember that the complement version of both 2 sets and 3 sets began that way. Well, this is the complementary version of pi, and I'm going to spend some time trying to explain to you why this result is valid. So here is a proof of the complementary version of this particular principle, or the principle of inclusion and exclusion. Let me write down the basics of this, because it's difficult for me to keep switching the pages. So this is the left-hand side of the equation, and in the right-hand side I had I subset of square bracket n, which, let's remind ourselves, is the set 1 through n, and now I have minus 1 to the power cardinality of I multiplied by the size of a sub I. And let me write this down, where a sub I is simply by definition all these ai's intersected where I belongs to I. And we have the convention. Let me write this in bracket. This formula does not apply when I is empty set, so I have to define it separately, and I call A empty set as X. So this is what we have to prove. Now, this is a slightly different proof from what you've seen before. The topic is slightly more advanced, perhaps, than what a school syllabus has. And if at all you've seen results like this, you've seen it applied to 2 or 3 sets. The moment you generalize things to any number of sets, things become more complicated. So I'll attempt to try and explain to you how you might think about this or how you might prove this in the general context. It takes a while actually to simply understand what this formula is about. So I would expect you to go back and rerun this, look at this more carefully, write it down, examine this more carefully, look at the case n equal to 2 and n equal to 3, and see if you can justify the fact that whatever is said here in the general case matches what we wrote for n equal to 2 and n equal to 3. Now, if I may start the proof, the idea of the proof is the following. The left-hand side and the right-hand side both count things. So at the end of the day, what we will do is we will look at an element x, which is an x. And we will decide for each x in x how many times it appears on the left-hand side and how many times it appears on the right-hand side. If we can show or see that each x in x, and we never go outside x because that's the universe, if we can see or show that each x in x appears on the left-hand side as many times as it appears on the right-hand side, then we would have proven the 2 statements. It's something like saying x is on the left-hand side precisely when x is on the right-hand side. So you tick a yes to x on the left-hand side means ticking or checking the box yes on the right-hand side as well. So there are 2 situations here, 2 cases to deal with. So I begin with x is an x. My case 1 is when x does not belong to the union of the AIs. It goes without saying that x is an x. There's nothing outside that. Well, it's straightforward that if x is not in the union of the AIs, then it is in the complement of the union of the AIs, and therefore it contributes 1 to the right-hand side. So I'm simply going to write contributes. I better write plus because I have the danger of having minuses on the right-hand side. Contributes plus to the right-hand side, sorry, to the left-hand side. This is straightforward. So I'm taking those elements x which are in none of the AIs. Therefore, they are in the complement or they're in x set difference, the union, and therefore they appear once. In other words, all those x's which satisfy x does not belong to the union of the AIs add 1 to the left-hand side. So if there are 5 such x's, the left-hand side is 5. And there's 10 such x's, then the left-hand side is 10. What happens to the right-hand side? Well, what is the right-hand side? If you spell out the right-hand side, and I never actually did, I wrote it in the compact form. But if I were to try to write this right-hand side out, corresponding to I equal to the empty set, you have minus 1 to the power 0, which is plus 1, size of a sub empty set, which is the size of x. Then I have a bunch that comes with a minus sign. This bunch looks like, and I'm going to write the notation summation. The minus corresponds to taking things one at a time. I'm going to write the AIs. And I'm not going to write this summation over. It's always I from 1 to n. Then I'll have a bunch that has a plus. This is an AI intersect an AJ, I not equal to j. And then I have a minus something, and there's a plus something, and so on and so forth. For case 1, this is enough for me to write down. Now, x is in none of the AIs. Therefore, it will contribute nothing to this, to this, to this, or to this, and only contribute something to this. And what will it contribute? Contribute 1 to x, because every x is an x. Every x is in the set x. So therefore, the contribution of any element x which is in none of the AIs is precisely the same to the left-hand side and the right-hand side. Therefore, I'm done for those x's which belong to none of the AIs. Now, let me go to case 2. I've unfortunately used up a lot of this paper here, so I'll kind of have to rewrite some of this. But let me write down what is case 2 first. So in case 2, I'm assuming x does belong to the union of the AIs. Because I want to do this in one shot, let me suppose x belongs to exactly k of the n sets a1, a2, a3 till an. And what am I assuming about k? That k is at least 1 and k is no more than n because there are no more than n sets to take. So for this argument, I'm assuming that k is fixed, arbitrarily chosen between 1 and n. So x is any element. It belongs to k of the sets. It doesn't really matter which k sets I pick. Let me, for the sake of simplicity, let me write for simplicity. Suppose that x belongs to the first k sets, a1, a2, ak. If they belong to some other collection of k sets, you could always argue that I could renumber the sets. And the k sets that x belongs to are now renumbered to be called a1 to ak. So now let me rewrite what I wrote for the right-hand side. The right-hand side was x minus, and then I had a bunch that looked like this, taken one at a time. Then I had a plus with ai intersection aj, taken two at a time. And then minus taken three at a time. And then plus taken four at a time, and so on and so forth. I'm just going to let it be there. Now, what is the contribution of x to the right-hand side? Is. Now, does x contribute to x? The answer is yes. So this is plus 1 or just 1. Does it contribute to the second term out here, which is summation taken one at a time? The answer is sometimes. How often does it contribute? Well, it will contribute to a1 and to a2 and to a3 and so on till ak. But beyond ak, it will contribute nothing. So the contribution to the second term is minus k. 1 for each of the first k sets, since I've relabeled it, and none to the remaining n minus k. What happens to the third term, the places where I've taken two at a time? Well, this is a little trickier now. Well, if x has to belong to ai intersection aj, it must belong to both of them. So therefore, if I choose my subscripts I and j to both lie within the first k numbers, then and only then will I have a contribution 1 to x. In other words, x will contribute plus 1 to ai intersection aj cardinality if and only if I and j are both chosen from within the first n numbers, first k numbers. Therefore, the contribution will be as much as the number of ways in which I can pick two distinct elements, I and j, from the first k numbers. We know this to be the binomial coefficient k choose 2. The third term is similar. The third term, which I haven't explicitly written down, involves taking numbers 3 at a time, sets 3 at a time, and therefore I will get k choose 3, and so on and so forth. Having done the binomial theorem, you would recognize that this is the expansion of 1 minus 1 to the power of k. And because I'm assuming k is not 0, 1 minus 1 to the power of k is in fact 0. What have we concluded? We've concluded that whenever I take x to be in the union of the AIs and in particular belonging to k of these sets, where k is at least 1, the contribution of x to the right-hand side is 0. On the other hand, it is more obviously 0 to the left-hand side, because the left-hand side is the set which is the complement of the union of the AIs, and x is not in that complement. X is in the union of the AIs. So obviously the contribution of x to the left-hand side is also 0. So contribution of x to the left-hand side is more obviously 0. And therefore, that completes what we wanted to say. I'm going to close today's lecture by telling you the direct version of pi. So let me close up by giving you the direct version of pi, which is in fact how I started my lecture. The direct version and the indirect version, or the complementary version, are very, very similar. In fact, you can derive one from the other. You can see that the left-hand side deals with the size of the union of the sets, and the right-hand side is very similar to what the right-hand side of the complement version was. In fact, I leave this as an exercise for you to figure this out from the complementary version. The left-hand side is simply the number of elements in X minus the unions from the complementary version. And if you take the first term away from the complementary version, that is the size of X. So if you take the complementary version and subtract the number of elements in X from both sides, what you get is the direct version. Thank you for listening to this lecture. And in my second lecture, I'll give you examples where I use the principle of inclusion exclusion, typically in the complementary version.